Imagine waking up tomorrow morning, and the alarm goes off at 6:45, just like it always does. You reach over, silence it, and lie there for a moment in that half-conscious haze, thinking about coffee, thinking about your commute, thinking about the ordinary, unremarkable rhythm of another day. Then you pull back the curtain, and instead of the pale gold wash of early morning light beginning to climb the horizon, there is nothing. Absolute, total, impenetrable darkness. Not the darkness of a cloudy night, not the darkness of a power outage, but a darkness so complete and so wrong that your brain refuses to process it for a full 2 or 3 seconds. Your heart rate doubles before you even understand why. And then, slowly, the realization creeps in like cold water seeping under a door. The sun is gone. Not obscured. Not eclipsed. Gone. Think about that for a moment. Really sit with it. Because what we are about to explore together is not a fantasy, not a fairy tale, and not a cheap science fiction premise. It is one of the most carefully studied, scientifically modeled, intellectually provocative thought experiments in the history of human inquiry. What would actually happen, minute by minute, hour by hour, if our sun simply ceased to exist for 24 hours? And the answers, drawn from astrophysics, climatology, biology, geology, psychology, and even philosophy, are far more strange, far more terrifying, and far more fascinating than almost anything you've ever heard before. Because here is the thing that most people get wrong when they first hear this question. They assume the worst would happen immediately. They picture the Earth plunging into cold, into chaos, into some kind of instant apocalypse. But the truth is so much more layered, so much more surprising, and in many ways so much more unsettling than that. Some of the consequences would be instantaneous. Some would take minutes. Some would take hours. And some would not arrive until long after the 24 hours were up, rippling outward through time like the aftershocks of an earthquake that no seismograph was designed to measure. And here is perhaps the most haunting question of all, the one that should make the hairs on the back of your neck stand up just a little bit. If the sun disappeared right now, at this exact moment, how long would it take you to know? How long before anyone on Earth knew? The answer to that question alone is enough to fundamentally rewrite the way you think about the universe, about light, about distance, and about the terrifyingly fragile thread by which everything you love hangs suspended in the void of space. So let us begin. Let us go through this together, second by second, minute by minute, hour by hour. Let us imagine the sun is gone. Not forever, just for 24 hours. And let us see, with rigorous scientific honesty and unflinching curiosity, exactly what that means for the only world we have ever called home. But first, to understand what losing the sun means, we need to understand what having the sun means. And not in the vague, hand-wavy way that we throw around phrases like, the sun gives us life, without ever really stopping to think about what that means in practical, physical, molecular terms. Because the sun is not simply a source of light and warmth. It is the architect of nearly every system on Earth that makes complex life possible. It is the engine beneath the engine. It is the reason water flows, the reason wind blows, the reason you are alive to read these words. Let us start with the basics and then go deeper, because the deeper we go, the more extraordinary it becomes. The sun is, at its core, a massive nuclear fusion reactor. Every second of every day, it converts approximately 600 million tons of hydrogen into helium through a process of thermonuclear fusion at its core, where temperatures reach 15 million degrees Celsius. In doing so, it releases an almost incomprehensible amount of energy, roughly 3.8 times 10 to the power of 26 watts every single second. To put that in perspective, if you could somehow capture just 1 second's worth of the sun's energy output, it would be enough to power the entire United States of America for approximately 9 million years. That is not a typo. 9 million years. From 1 second of sunlight. That energy radiates outward from the sun's core, but it does not travel quickly. In fact, A photon of light born in the sun's core might take between 10,000 and 100,000 years to work its way through the dense plasma of the solar interior before it finally reaches the sun's surface, the photosphere, and is released into space. Then, once free, it travels the roughly 149 million kilometers between the sun and the Earth in about 8 minutes and 20 seconds. 8 minutes and 20 seconds. That is the famous light delay. And it is the first answer to our haunting question. If the sun disappeared right now, you would not know for 8 minutes and 20 seconds. You would keep seeing the sun in the sky, keep feeling its warmth, keep living in a world that appeared completely normal, for 8 minutes and 20 seconds after it ceased to exist. And this is not a technicality. This is not a philosophical footnote. This is a fact about the physical universe that should stop you in your tracks. Right now, at this very moment, everything you see when you look at the sun is ancient news. The sun you are looking at is the sun as it was 8 minutes and 20 seconds ago. You are always living in the sun's past. You have never seen the sun as it truly is, right now, in this moment. No human being ever has. Now, there is something even stranger waiting just beneath the surface of that fact, and it concerns not light, but gravity. And this is where the thought experiment gets genuinely, philosophically complicated, because it touches on one of the great unresolved questions at the frontier of modern physics. When we ask what would happen if the sun disappeared, we are also implicitly asking, what would happen to Earth's gravity? Would Earth's orbit collapse instantly? Would it fly off into space in the same moment the light went out? Or would there be a delay? According to Einstein's general theory of relativity, gravity is not an instantaneous force. It propagates at the speed of light. This is one of the most counterintuitive and remarkable results of Einsteinian physics, and it stands in direct contrast to Newton's older model, in which gravity was understood as an instantaneous action at a distance. Einstein showed that space-time is a fabric, and that massive objects like the sun warp and curve that fabric, creating what we experience as gravity. When a massive object moves or disappears, that distortion does not instantly vanish across all of space. Instead, it propagates outward as gravitational waves at the speed of light. This means that if the sun disappeared, Earth would continue to orbit the now empty point in space where the sun had been for exactly 8 minutes and 20 seconds. For those 8 minutes and 20 seconds, Earth would orbit a ghost. It would be pulled along a curved path by the gravitational memory of a star that no longer existed. And only when the last gravitational wave front from the sun's disappearance reached Earth, at precisely the same moment the last photon of sunlight winked out and the sky went dark, would Earth's orbit be released. At that moment, Earth would stop orbiting and continue in whatever direction its velocity carried it, flying outward into interstellar space in a straight line, like a ball on a string the moment you let go. Now, here is your first question to ask yourself at home. How would it feel in those 8 minutes and 20 seconds before you knew? You would be going about your normal morning, perhaps making coffee, perhaps getting the kids ready for school. And all of it would be happening in a world where the sun was already gone, and you had no idea. The universe would already be changed. The clock would already be ticking, and you would be blissfully, completely unaware. What does that say about how much we actually know about the universe around us at any given moment? How many things are already different, already changed, already gone, that we simply haven't received the news about yet? Because light is not instantaneous. Because information travels at a finite speed. Because the universe is big enough that we are always looking at the past, we are never truly aware of the present state of the cosmos. The star you see shining tonight might have gone supernova 1,000 years ago. You would not know for another 1,000 years. The universe is full of dead things that still appear to be alive, and living things whose light has not reached us yet. We exist in a kind of permanent informational lag, separated from the true present by the immutable speed of light. Let us come back to Earth now, to that moment 8 minutes and 20 seconds after the sun's disappearance, when the last photon of sunlight fades from the sky and darkness falls across the entire planet. Not night, not dusk, not twilight, darkness. Total, absolute darkness across every surface of the Earth that was previously facing the sun. The day side of the planet would plunge into the same kind of darkness as the night side. No stars initially, because the human eye takes time to adjust from full daylight to starlit darkness. Drivers on highways would suddenly have no visibility. Pilots mid-flight would lose visual reference to the horizon. Anyone operating in daylight would be suddenly, catastrophically blind. The first few seconds would be absolute chaos. Traffic accidents would spike in every city, every highway, every country on the day side of the planet. Planes would switch to instruments. Emergency systems would activate. People would reach for their phones, turn on flashlights, start screaming. Social media would erupt. Emergency services would be overwhelmed. And all of this within the first 30 seconds. Think about where you are right now. If it is daytime where you live, imagine the light going out. Just off like a switch. No warning. No flicker. Just darkness. What would be the first thing you'd do? What would the person next to you do? And multiply that by 4 billion people simultaneously experiencing the exact same thing. But here is the thing. The darkness, as terrifying as it is not even close to the most dangerous thing that happens in the first minutes. Because sunlight is not just light. It is energy. Radiant energy, pouring down on Earth at a rate of about 1,361 watts per square meter at the top of the atmosphere. And that energy is what drives weather systems, ocean currents, the jet stream, and ultimately the atmospheric engine of the entire planet. The moment that energy source is cut off, the atmospheric engine begins to slow. Not instantly, because the Earth has enormous thermal inertia, meaning it has stored an enormous amount of heat in its oceans, its land masses, its atmosphere. But the process begins immediately. The temperature at the Earth's surface would not drop dramatically in the first few minutes. The thermal inertia of the system is too great for that. But the direction of change would be unmistakable from the very first moment. The surface would begin to cool, slowly at first, maybe a fraction of a degree in the first hour. But the slope would be downward relentlessly, without any possibility of reversal until the sun returned. Scientists have modeled this, and the results are both fascinating and disturbing. Within the first 24 hours, surface temperatures across most of the planet would drop by an average of somewhere between 20 and 30 degrees Fahrenheit, which is roughly 11 to 17 degrees Celsius. That might not sound catastrophic. It sounds like a cold week. But here is what makes it genuinely dangerous. The rate of cooling is not uniform, and it is in the variation, in the differentials, in the sudden violent gradients between warm and cold zones, that real destruction begins. The oceans, for example, would cool far more slowly than the land. Water has one of the highest specific heat capacities of any common substance, meaning it takes an enormous amount of energy loss to reduce its temperature. This would create wild temperature differentials between the ocean surface and the land surface, driving unprecedented wind patterns. The atmospheric circulation systems we know, the trade winds, the westerlies, the jet stream, are all ultimately powered by temperature differentials caused by unequal heating of the Earth's surface by the sun. Remove the sun, and those differentials do not vanish immediately. They change. They shift. And in shifting, they could generate some of the most violent and unusual weather patterns ever seen. Storm systems of extraordinary power could form at the boundaries between still warm ocean air and rapidly cooling land air. Winds that we cannot precisely predict in direction or intensity because they would be unlike any wind pattern in the historical record. The meteorological models we use to predict weather are calibrated against a world with a functioning sun. They break down when you remove that input. And what about the oceans themselves? The surface layers of the ocean, which are warmed by the sun and drive thermohaline circulation, the great conveyor belt of ocean currents that moves heat around the planet, would begin to cool. The Gulf Stream, the Kuroshio Current, the Antarctic circumpolar current, all of them would begin to feel the absence. Not immediately. Not in 24 hours. The oceans are slow. But the beginning of the disruption would start in the very first hours of darkness. Now let us think about plants. Because plants are perhaps the most immediately and directly threatened by the removal of sunlight. Photosynthesis, the process by which plants convert carbon dioxide and water into glucose and oxygen using the energy of sunlight, would stop. Not slow down. Stop. The moment photons cease to arrive, the photosynthetic machinery in every leaf, every blade of grass, every microscopic phytoplankton in the ocean, would halt. In humans and animals, this might be analogous to the heart stopping. It is that fundamental to the organism's metabolism. But here is what many people do not realize. Plants are surprisingly resilient to short-term darkness. They have evolved in a world where darkness comes every single night. They have internal biological clocks, circadian rhythms, that anticipate and manage periods of darkness. A single night, or even 2 or 3 nights, does not kill most plants. They have stored energy reserves, starches and sugars in their cells that they can draw on during periods without light. The question is how long those reserves last and how rapidly the temperature drop affects cell function. In a 24-hour scenario, most plants would survive. The metabolic stress would be significant. Some faster metabolizing tropical species might show signs of strain, but the majority of the plant kingdom would endure. It would be like a very cold, very dark, very long night. Uncomfortable, stressful, but survivable. The organisms that would suffer most immediately and most severely would be the phytoplankton in the surface layers of the ocean. These microscopic photosynthetic organisms are often called the lungs of the Earth because they produce somewhere between 50 and 80% of the oxygen in Earth's atmosphere. They are also the base of the oceanic food web. Without them, nothing else in the ocean can survive for long. And because phytoplankton are so sensitive to light, and because their reproduction rates are tied to light availability, even a 24-hour disruption would create measurable consequences. Not catastrophic ones at the 24-hour mark, but measurable ones, important ones, and ones that would have cascading implications that we will return to. But ask yourself this question now, because it is one worth sitting with. How much of your life is built on the sun? Not just your survival, but your civilization, your culture, your daily experience. Think about electricity. A significant portion of the world's electricity is generated by hydroelectric power, which depends on water cycling through the atmosphere driven by solar energy. Solar panels, obviously, would go dark instantly. But even the coal and natural gas power plants, which would keep running, are burning ancient sunlight. Fossil fuels are nothing more than the compressed, transformed remains of ancient organisms that captured the sun's energy millions of years ago. Every time you burn gasoline, you are releasing light that fell on the Earth during the Carboniferous period. 300-million-year-old sunlight, stored in carbon, released in your engine. The sun is so deeply woven into the fabric of human civilization that even our fire is made of it. The electrical grid would experience extraordinary stress in the first hours. Power demand would surge because the darkness, combined with the dropping temperatures, would send people scrambling for artificial heat and light. At the same time, solar generation would instantly go to zero. Wind generation might actually increase initially as the unusual weather patterns generate stronger winds, but the variability would make those gains unpredictable and hard to distribute. Nuclear power plants would keep running. Hydroelectric plants would keep running. Coal and gas plants would keep running. But the sudden massive increase in demand, combined with the loss of solar generation, would create serious stress on the grids of countries that rely heavily on solar. In sunny, equatorial nations that have been transitioning aggressively to solar power, this would be a genuine crisis. And in parts of the developing world, where grid infrastructure is already fragile, the darkness and cold could create humanitarian emergencies within the first few hours. As hospitals lose backup power, as water treatment plants fail, as communication networks begin to drop. And now let us talk about something that most people have never even thought about in the context of this scenario. Let us talk about what happens to the magnetic field. Because the Earth's magnetic field, the invisible shield that protects us from the most lethal effects of the solar wind, is not directly created by the sun. It is generated by the churning of Earth's liquid iron outer core, a process called the geodynamo. The magnetic field is our own. It belongs to us. It does not need the sun to exist. But the solar wind, the stream of charged particles that constantly flows outward from the sun, is responsible for shaping the magnetosphere, the region of space around Earth dominated by our magnetic field. The solar wind compresses the magnetosphere on the sunward side and stretches it into a long tail on the downwind side. In the absence of the sun, the solar wind would disappear too. No solar wind means no compression, no shaping. The magnetosphere would relax into a more symmetrical, spherical shape. And without the solar wind constantly hammering at it, the magnetosphere would actually expand. Storm systems of extraordinary power could form at the boundaries between still warm ocean air and rapidly cooling land air. Winds that we cannot precisely predict in direction or intensity because they would be unlike any wind pattern in the historical record. The meteorological models we use to predict weather are calibrated against a world with a functioning sun. They break down when you remove that input. And what about the oceans themselves? The surface layers of the ocean, which are warmed by the sun and drive thermohaline circulation, the great conveyor belt of ocean currents that moves heat around the planet, would begin to cool. The Gulf Stream, the Kuroshio Current, the Antarctic Circumpolar Current, all of them would begin to feel the absence. Not immediately. Not in 24 hours. The oceans are slow. But the beginning of the disruption would start in the very first hours of darkness. Now let us think about plants. Because plants are perhaps the most immediately and directly threatened by the removal of sunlight. Photosynthesis, the process by which plants convert carbon dioxide and water into glucose and oxygen using the energy of sunlight, would stop. Not slow down. Stop. The moment photons cease to arrive, the photosynthetic machinery in every leaf, every blade of grass, every microscopic phytoplankton in the ocean, would halt. In humans and animals, this might be analogous to the heart stopping. It is that fundamental to the organism's metabolism. But here is what many people do not realize. Plants are surprisingly resilient to short-term darkness. They have evolved in a world where darkness comes every single night. They have internal biological clocks, circadian rhythms, that anticipate and manage periods of darkness. A single night, or even 2 or 3 nights, does not kill most plants. They have stored energy reserves, starches and sugars in their cells that they can draw on during periods without light. The question is how long those reserves last and how rapidly the temperature drop affects cell function. In a 24-hour scenario, most plants would survive. The metabolic stress would be significant. Some faster metabolizing tropical species might show signs of strain. But the majority of the plant kingdom would endure. It would be like a very cold, very dark, very long night. Uncomfortable, stressful, but survivable. The organisms that would suffer most immediately and most severely would be the phytoplankton in the surface layers of the ocean. These microscopic photosynthetic organisms are often called the lungs of the Earth because they produce somewhere between 50 and 80% of the oxygen in Earth's atmosphere. They are also the base of the oceanic food web. Without them, nothing else in the ocean can survive for long. And because phytoplankton are so sensitive to light, and because their reproduction rates are tied to light availability, even a 24-hour disruption would create measurable consequences. Not catastrophic ones at the 24-hour mark, but measurable ones, important ones, and ones that would have cascading implications that we will return to. But ask yourself this question now, because it is one worth sitting with. How much of your life is built on the sun? Not just your survival, but your civilization, your culture, your daily experience. Think about electricity. A significant portion of the world's electricity is generated by hydroelectric power, which depends on water cycling through the atmosphere driven by solar energy. Solar panels, obviously, would go dark instantly. But even the coal and natural gas power plants, which would keep running, are burning ancient sunlight. Fossil fuels are nothing more than the compressed, transformed remains of ancient organisms that captured the sun's energy millions of years ago. Every time you burn gasoline, you are releasing light that fell on the Earth during the Carboniferous period. 300-million-year-old sunlight, stored in carbon, released in your engine. The sun is so deeply woven into the fabric of human civilization that even our fire is made of it. The electrical grid would experience extraordinary stress in the first hours. Power demand would surge because the darkness, combined with the dropping temperatures, would send people scrambling for artificial heat and light. At the same time, solar generation would instantly go to zero. Wind generation might actually increase initially as the unusual weather patterns generate stronger winds, but the variability would make those gains unpredictable and hard to distribute. Nuclear power plants would keep running. Hydroelectric plants would keep running. Coal and gas plants would keep running. But the sudden massive increase in demand, combined with the loss of solar generation, would create serious stress on the grids of countries that rely heavily on solar. In sunny, equatorial nations that have been transitioning aggressively to solar power, this would be a genuine crisis. And in parts of the developing world, where grid infrastructure is already fragile, the darkness and cold could create humanitarian emergencies within the first few hours. As hospitals lose backup power, as water treatment plants fail, as communication networks begin to drop. And now let us talk about something that most people have never even thought about in the context of this scenario. Let us talk about what happens to the magnetic field. Because the Earth's magnetic field, the invisible shield that protects us from the most lethal effects of the solar wind, is not directly created by the sun. It is generated by the churning of Earth's liquid iron outer core, a process called the geodynamo. The magnetic field is our own. It belongs to us. It does not need the sun to exist. But the solar wind, the stream of charged particles that constantly flows outward from the sun, is responsible for shaping the magnetosphere, the region of space around Earth dominated by our magnetic field. The solar wind compresses the magnetosphere on the sunward side and stretches it into a long tail on the downwind side. In the absence of the sun, the solar wind would disappear too. No solar wind means no compression, no shaping. The magnetosphere would relax into a more symmetrical, spherical shape. And without the solar wind constantly hammering at it, the magnetosphere would actually expand. And then, 8 minutes and 20 seconds after the sun's disappearance, something else would happen that no instrument on Earth had ever recorded before. Gravitational wave detectors like LIGO in the United States and Virgo in Europe would register something. A gravitational wave signal propagating outward from the sun's location. When a massive object suddenly disappears, the change in the curvature of space-time it was creating propagates outward at the speed of light as a gravitational wave. The kind of signal LIGO was designed to detect comes from objects far more massive and far more violent, from colliding black holes and neutron stars. The sun's disappearance would generate a signal of a different character. Whether our current instruments would be sensitive enough to detect it is a genuinely interesting scientific question. Some physicists believe they might. This would be the universe's equivalent of a starting gun going off. The gravitational fingerprint of the sun's disappearance, written in the fabric of space-time itself. Now let us spend some time talking about what is perhaps the most scientifically surprising aspect of this scenario. Something that appends the intuitive assumption that everything would immediately get worse. Because in some ways, and in some places, the immediate hours of darkness would create conditions that are scientifically extraordinary and even beautiful. The immediate darkness would allow astronomical observations of a kind that have never been possible from Earth's surface. Because the sun's scattered light in our atmosphere, what we call airglow, and the direct glare of the sun during the day prevent us from observing most of the sky most of the time. But with the sun gone, The entire sky would be available for observation, day and night, simultaneously, from every point on Earth's surface. The day side of the planet would suddenly have access to the night sky. The full celestial sphere would be visible. Telescopes that normally have to wait for night would be operational around the clock. For astronomers, this would be the most extraordinary observing opportunity in human history. And the view would be stunning. Without the sun to scatter light in our atmosphere, the sky would be darker than it has ever appeared to human eyes in recorded history. Assuming the atmosphere itself is clear and not full of dust or clouds, the density of stars visible would be breathtaking. The Milky Way would be visible from suburban areas in the middle of what used to be the afternoon. Planets would shine with a clarity rarely seen except from the highest and driest mountain observatories. The zodiacal light, normally a faint cone of sunlight scattered by interplanetary dust, would vanish, making the sky even darker. Distant galaxies visible only through telescopes might be accessible to keen-eyed observers with binoculars. There is something deeply poetic about this. In the moment of the sun's absence, the cosmos beyond would be more visible than ever before. The loss of the nearest star would make the rest of the universe more legible. It would be as if the sun had been a kind of brilliant, beautiful blindfold, and without it, the infinite depth of space would open up around us. This is not a metaphor. It is a physical description of what would actually happen. But let us be honest with ourselves. For the vast majority of people, this beauty would be inaccessible. Because most people would not be standing outside with binoculars, appreciating the newly visible Andromeda galaxy. Most people would be terrified. They would be huddled indoors, burning whatever fuel they had, trying to keep warm, trying to contact loved ones, trying to understand what was happening. The psychological state of humanity during this event would be dominated not by wonder but by fear. Let us think carefully now about what happens in the animal kingdom. Because we tend to focus on human responses to dramatic events, but the non-human world would be profoundly affected in ways that are scientifically fascinating and, in some cases, tragically beautiful. Animals that use the sun for navigation and circadian rhythm regulation would be immediately disrupted. Birds that navigate by the position of the sun would suddenly be flying by other means, using magnetic field detection, star patterns, and learned landmarks. Migratory birds in mid-flight would be among the most immediately disoriented. Species of birds that use time-compensated sun compass orientation, which is a mechanism that uses the sun's position adjusted for time of day to determine direction, would suddenly lose their primary navigational reference. For migrating flocks, this could mean becoming lost in ways that make subsequent navigation extremely difficult. Nocturnal animals would behave very strangely. Owls, bats, raccoons, and other creatures adapted to darkness would become active during what their internal clocks told them should be daytime. Without the light cue to suppress their nocturnal behavior, many would emerge prematurely, not understanding that this darkness was different from ordinary night. Some species of owls might simply begin a second active cycle, hunting, as they do every night. But other species would be confused by the absence of a transition, the gradual dimming of light that normally tells them it is safe to emerge. Honeybees would be among the most immediately affected. Bees use the sun as a primary navigation reference, and their waggle dance, the famous communication system by which scout bees tell hive mates the direction and distance of food sources, is calibrated to the sun's position. With the sun gone, this entire communication system would break down. Forager bees out in the field would suddenly lose their navigational reference and might fail to return to the hive. This would not kill hives within 24 hours, but it would create measurable disruption in foraging behavior. Marine animals that depend on light for critical behaviors would also be affected. Coral reef fish that are active during the day would retreat to their nighttime refuges. Filter feeders and other animals that use light cues to regulate their behavior would be confused. Many species of plankton undergo vertical migration in the water column, moving up toward the surface during the day to photosynthesize and down at night to avoid predators. This behavior, called diel vertical migration and representing one of the largest daily movements of biomass on Earth, would be thrown into disorder. But perhaps the most profound animal response would be among the great apes. Chimpanzees, gorillas, orangutans, our closest evolutionary relatives, whose cognitive and emotional lives most closely mirror our own, would have a response to sudden total darkness in the middle of the day that researchers believe would include behaviors very similar to those seen in human populations. Distress vocalizations, social clustering, attempts to find shelter. The primatological literature on responses to unexpected stimuli, including unexpected darkness during solar eclipses, shows that chimpanzees in particular respond to sudden daytime darkness with what researchers describe as rhythmic rocking, charging behavior, and intense social bonding. In other words, they gather together. They huddle. They comfort each other, not unlike what many human beings would also do. And is that not something worth pausing on? In the moment of a cosmic catastrophe, humans and chimpanzees would respond in fundamentally the same way. They would reach for each other. They would seek the warmth of another living body in the cold darkness. Whatever our differences, whatever our cultural, linguistic, and intellectual distance from our primate cousins, we share with them the oldest response to darkness: the need for company, the need to not be alone in the dark. Let us now explore the specific mechanics of temperature change during the 24-hour darkness in more detail, because this is where the scientific modeling gets genuinely sophisticated and where the implications are most varied and most surprising. The Earth is not a uniform surface. It is a patchwork of radically different environments, from the steaming tropics to the frozen poles, from sun-scorched deserts to temperate forests to high-altitude plateaus. Each of these environments would respond to the absence of sunlight differently, and the differences would be dramatic. Let us start with the tropics. Equatorial regions receive the most intense solar radiation on Earth. A location near the equator might receive close to a full 1,360 watts per square meter of solar energy on a clear day. That is an enormous amount of energy input, and it is what drives the extraordinary biological richness and the intense weather patterns of tropical regions. Remove that energy input, and equatorial temperatures would drop faster, in absolute terms, than temperatures in temperate regions, even though temperate regions start from a lower baseline. Within 24 hours, surface temperatures in tropical regions could drop by 30 to 40 degrees Fahrenheit. The Amazon rainforest, normally a place of oppressive heat and humidity, could find itself at temperatures approaching or even reaching freezing at ground level. This is not a scenario the tropical biome has ever experienced. Tropical plants have not evolved to handle sub-zero temperatures. Their cellular membranes, calibrated for warmth, would rupture as ice crystals formed inside them. Tropical insects, poikilotherms that regulate their body temperature through the environment rather than internal metabolism, would slow dramatically and might become immobile. Many would die if temperatures fell below their lower survival thresholds. The most biodiverse ecosystems on Earth, the tropical rainforests, would be on the knife's edge within the first 24 hours. Meanwhile, in the polar regions, where temperatures are already well below zero, the additional cooling from the absence of solar input would be less dramatic in absolute terms. Antarctica in winter already receives essentially no solar energy. It is already at the thermal floor of what the solar-removed Earth would experience. The change would be relatively small. Perhaps another 5 to 10 degrees Celsius of cooling over 24 hours. Cold enough to be dangerous in the context of human operations there, but not a fundamental departure from the existing conditions. The most striking temperature responses would occur at mid-latitudes, in the temperate zones of Europe, North America, Asia, and Australasia, where the solar energy input is significant but moderate, and where the thermal inertia of the environment is balanced between the extremes of the tropics and the poles. These regions would experience cooling on the order of 15 to 25 degrees Fahrenheit over 24 hours. Enough to be profoundly uncomfortable but not immediately lethal for most people with shelter and warmth. The challenge would be in the margins, for the homeless, for the elderly, for those in inadequate housing, for people in poorly insulated structures in regions that do not normally experience such cold. And here is an angle that is almost never considered in popular discussions of this scenario. What happens to the water cycle? Because the water cycle is one of the most sun-dependent systems on Earth, and yet it is so fundamental to human civilization that any disruption to it has cascading consequences that ripple out in every direction. The water cycle, also known as the hydrological cycle, is driven by solar energy. The sun heats water in the oceans, lakes, rivers, and on land, causing it to evaporate. This water vapor rises into the atmosphere, cools, condenses into clouds, and falls as precipitation, rain, or snow, which then flows back into rivers and oceans and begins the cycle again. It is a system of extraordinary elegance, and it is what keeps fresh water accessible in lakes, rivers, and aquifers around the world. Remove the sun, and the evaporation step slows dramatically. The water cycle begins to shut down. Within 24 hours, the effects would be subtle but directional. Less water would be evaporating from the surface. The existing moisture in the atmosphere would continue to cycle through, producing weather systems. But the input of new moisture into the atmosphere would be diminished. Over time, if the darkness continued, this would result in progressive drying of the atmosphere and a reduction in precipitation. But within 24 hours, the existing atmospheric moisture would still be driving weather systems. In fact, as we noted earlier, the unusual temperature differentials would likely increase the intensity of some weather systems in the short term, even as the long-term trend pointed toward drying. Snow, interestingly, might actually increase in many mid-latitude regions within the first 24 hours, as the temperature drops push borderline precipitation events from rain into snow. This would be an eerie and beautiful sight. Snow falling in the darkness, visible only in the glow of streetlights and emergency lighting, falling on gardens that had been green and blooming just hours before. Now let us go somewhere unexpected. Let us go underground. Because beneath the surface of the Earth, in the complex and varied underworld of caves, groundwater systems, and deep rock formations, the absence of sunlight would initially mean almost nothing. The thermal environment of deep caves is extraordinarily stable, maintained by the geothermal heat that flows upward from the Earth's interior. A cave 200 meters underground might have a year-round temperature of 12 to 14 degrees Celsius, regardless of what is happening at the surface. The organisms that live in this environment, the cave-adapted species like blind cavefish, cave crickets, cave spiders, and the extraordinary microbes that subsist on chemosynthesis rather than photosynthesis, would be utterly unaffected. And this is perhaps one of the most remarkable things about life on Earth. The extraordinary diversity of metabolic strategies that evolution has discovered, most of which do not depend on the sun at all. Hydrothermal vent ecosystems at the bottom of the ocean, powered by chemical energy from the Earth's interior rather than sunlight, would continue without interruption. The bizarre and wonderful communities of tube worms, chemosynthetic bacteria, giant clams, and vent shrimp that populate these ecosystems would experience no change whatsoever. Their world has never seen the sun. Their world does not need it. They live by fire from below, not light from above. And this raises one of the most profound implications of this thought experiment, one that goes far beyond the question of what happens in 24 hours of darkness. It raises the question of what life really needs. We tend to think of life as inherently solar, as fundamentally dependent on the sun's energy. But the existence of chemosynthetic ecosystems, of organisms that have never seen a single photon of sunlight and yet thrive in rich, complex communities, tells us something extraordinary. Life is not inherently solar. Life is opportunistic. Life will exploit any available energy gradient, any source of chemical or thermal or electromagnetic energy it can find, and build a community around it. This has enormous implications for our search for life beyond Earth. Because if life does not require a sun, then the list of places in the universe where life might exist grows dramatically. The icy moons of the outer solar system, Europa, Enceladus, Titan, worlds where the surface is frozen and sunlight is dim and distant, might harbor life in their subsurface oceans, powered by tidal flexing and geothermal heat. The existence of life in Earth's deep oceans without sunlight is our strongest argument that life might exist in similar environments elsewhere. But let us return to the surface, to the human world, to the crisis unfolding above ground during those 24 hours. Because there is a dimension of this scenario that touches on something fundamental about human civilization and about the systems we have built to sustain billions of lives, and it is the question of food. Not food over the long term, not famine, which 24 hours is nowhere near long enough to create, but the immediate logistics of food access and the psychological relationship between darkness and hunger. Food systems are deeply sun-dependent, not just because food grows in the sun, but because the entire global supply chain that moves food from farm to table is powered by infrastructure that is, at every step, ultimately solar. Refrigeration, which keeps food from spoiling, requires electricity. Transportation, which moves food from where it is grown to where it is consumed, requires fuel. Industrial agriculture, which produces most of the world's food, requires machinery, fertilizers, pesticides, and water management systems, all of which depend on energy. Remove the sun, and the energy systems begin to strain. In 24 hours, no food in refrigerators or freezers would spoil, assuming the power stayed on. And for most developed world infrastructure, the power would stay on. Nuclear, coal, gas, and hydroelectric plants would keep running. The food supply would not be immediately threatened. But the psychological dimension of hunger and darkness is worth considering. Studies of food psychology have consistently shown that darkness increases appetite, particularly for comfort foods. People eat more in dimly lit environments than in brightly lit ones. Restaurants have exploited this for decades. A world plunged into unexpected darkness in the middle of the day would likely see a surge in comfort eating, in people cooking warming meals, in families gathering around kitchen tables with candles and hot food. This is not trivial. It is human. It is one of the ways we respond to fear and uncertainty. We feed ourselves and each other. Food, in this scenario, would become a social object in a way it usually is not. The act of preparing and sharing a meal in the darkness would be a form of reassurance, a statement of normalcy in an abnormal world. I am here. We are here. We are warm and fed and together. And everything will probably be all right. Probably. Now let us ask a more speculative question, one that takes us out of the well-established science and into the realm of considered speculation, where we should be very clear that we are extrapolating beyond what we can know for certain. What would happen to the political landscape of Earth during those 24 hours? How would governments, militaries, and international institutions respond to this event? This is of course deeply speculative, because the political response to any given crisis depends on an enormous number of contingent factors, including which governments happen to be in power, what their relationships with each other are, what pre-existing tensions and alliances exist at the moment the event occurs. But we can identify some general principles based on what we know about how governments respond to sudden, large-scale, poorly understood emergencies. The first response would almost certainly be military. Not aggressive military action, but defensive military posturing. The sudden, unexplained disappearance of the sun would, in the very first minutes, be indistinguishable from a catastrophic attack of some kind. No military force in the world has a contingency plan for the literal disappearance of the sun. But every major military force in the world has contingency plans for massive, unexpected electromagnetic disruptions, which is the closest analog. Those plans would be activated. NORAD would go to elevated alert. Russian strategic forces would increase readiness. Chinese military forces would mobilize. Indian, Pakistani, Israeli, and other nuclear-armed states would all go through the same defensive escalation, because in the absence of information, the worst case is always assumed. And then, as the hours passed and it became clear that this was not an attack, that there was no enemy, that this was something entirely outside the framework of human conflict, the military posture would shift. Not immediately relax, because militaries do not relax quickly, but shift toward something more like coordinated emergency response. International hotlines between heads of state, the famous direct communication channels between Washington and Moscow and Beijing that exist precisely for moments of maximum uncertainty and maximum danger, would be burning with activity. Scientists and military advisors would be in emergency briefings. The United Nations would convene an emergency session. There is a genuinely hopeful thread running through this speculation, and it is worth acknowledging. A crisis of this magnitude, one that was clearly not created by any human actor, one that threatened every nation equally regardless of wealth, ideology, or geography, might actually be one of the most powerful unifying forces the world had ever seen. The fragile international solidarity that emerged in the early days of the COVID-19 pandemic, before it was claimed by politics and nationalism, gives us a small and imperfect glimpse of what might be possible. A shared external threat, existential and universal, has historically been one of the most powerful drivers of human cooperation. The Apollo program was motivated in part by geopolitical competition, yes, but it also represented an extraordinary mobilization of collective human ingenuity in the face of a shared challenge. What might a world unified by 24 hours of sunless terror be capable of in the aftermath? But let us be honest. The same crisis would also bring out some of the worst impulses of human nature. Resource hoarding would begin almost immediately in some communities. People would start buying generators, fuel, candles, and food in quantities far beyond their immediate needs, driven by fear of what might come next. Supply chains for emergency goods would be overwhelmed within hours. In communities with pre-existing tensions, racial, economic, religious, or political, the stress of the darkness would provide a spark. Not everywhere, not even in most places, but somewhere. History teaches us that extreme stress and collective fear can strip away the thin veneer of civilization and expose the more primal, territorial instincts beneath. Here is a question to ask yourself. What would you do in those 24 hours? Would you reach out to your neighbors? Would you stockpile resources? Would you seek community, or would you seek solitude? Would you pray if you do that, or would you turn to science, or to art, or to another person? What you would do in those 24 hours says something important about who you are. And what billions of different people would do, each according to their own nature, their own fears, their own values, would make those 24 hours one of the most complex and revealing chapters in the history of human civilization. Let us now turn to something that we have been circling around without yet fully engaging, and that is the question of what happens when the sun comes back. Because the thought experiment specifies 24 hours. After 24 hours, the sun returns. And in some ways, the return is as interesting and as complicated as the departure. The first thing that would happen, in the instant the sun reappeared, would be what we might call the gravitational snap. The curved fabric of space-time around the sun's location would suddenly re-warp as the mass of the sun reappeared. This would propagate outward as another gravitational wave. Earth, which had been flying in a straight line for the past 8 minutes and 20 seconds since the first gravitational wave hit it, would be pulled back into orbit. But here is the critical question. Into what orbit? In 24 hours of flying free at its orbital velocity of approximately 30 kilometers per second, Earth would have traveled roughly 2.6 million kilometers from its previous orbital position. Not from the sun. Its distance from the sun would not have changed dramatically in the first 24 hours, because it would still be moving roughly along its previous orbital path, having been ejected tangentially. But its orbital angle around the sun would have changed. It would be in a slightly different part of its orbit than it would normally occupy on that date. When the sun reappears and gravity reasserts itself, Earth would be captured back into orbit. But it would be captured from a slightly different position with a slightly different velocity vector than it had when it left. This could mean that Earth's new orbit would be slightly different from its previous one. Whether the orbit would be slightly more elliptical, whether the period would be slightly different, whether the aphelion and perihelion would shift, would depend on the precise geometry of the situation at the moment of recapture. The changes would likely be small, Perhaps not large enough to be immediately catastrophic, but they would be there, and they would be permanent. The Earth would carry the scar of the Sun's 24-hour absence in the shape of its orbit for years, decades, perhaps centuries. And then the light would return. 8 minutes and 20 seconds after the Sun reappeared, the first photons would reach Earth. The sky would go from black to blinding in what would feel, to exhausted, dark-adapted eyes, like an explosion of light. Pupils that had been wide open in the darkness would be overwhelmed. Everyone on the day side of the planet would need to shield their eyes. The transition would be, physiologically and psychologically, as shocking as the initial darkness. The first light would also trigger an extraordinary cascade of biological responses. In plants, the photosynthetic machinery would activate almost immediately. Within seconds of the first photons reaching chloroplasts, the Calvin cycle and the light-dependent reactions would start running again. You could, in a very real sense, watch the plants wake up. The greenness of leaves, the result of chlorophyll absorbing red and blue light and reflecting green, would suddenly look different in the oblique, cold light of a sun returning from the bottom of a 24-hour absence. Birds would start calling. Crickets would stop. Animals that had been sleeping through the strange night would stir and wake. The dawn chorus, normally one of the most beautiful sounds in nature, would ring out across every forest on the planet simultaneously, as every bird that uses light as a cue for singing responded to the sun's return. This would be extraordinary to experience. A dawn chorus not from a narrow band moving westward with a terminator as it normally does, but from every direction at once, as birds across the entire dayside hemisphere responded to the same return of light. The warming would begin immediately too. But the return to normal temperatures would take far longer than the cooling. Physics is asymmetric in this way. The Earth cooled for 24 hours, losing heat from its entire surface to the empty dark of space. Rewarming requires the sun to actively add energy back, which happens much more slowly than the passive loss of heat to a cold universe. Depending on the region, it might take weeks or even months for temperatures to fully return to their pre-event norms. In the tropics, the recovery would be faster. At mid-latitudes, slower. At the poles, possibly not for an entire season. And the consequences of even 24 hours of unusual cold would ripple through ecosystems for months. Crops that had been killed or damaged by frost would not recover. Fruits and vegetables in the fields of the tropics that had been killed by unprecedented cold would be lost. While a 24-hour blackout is survivable for most ecosystems, the agricultural losses could be significant and would take an entire growing season to address. In regions dependent on a single crop season, this could translate to genuine food insecurity for a period of months. Insurance companies would face a reckoning unlike anything in their history. Every property that sustained frost damage, every vehicle involved in a darkness-related accident, every business that suffered losses from the power disruptions, every airline that had to ground flights, every hospital that had to run on emergency power, would be filing claims simultaneously. The financial cost of 24 hours without the sun, by any reasonable economic modeling, would run into the tens of trillions of dollars globally. It would be the most expensive single event in the history of human civilization, far exceeding the cost of any war or any natural disaster on record. But let us, for a moment, rise above the immediate crisis and think about what this event would mean in the longer arc of human history. Because crises of this magnitude do not just cause damage. They also cause change. They force reckonings. They reveal the hidden assumptions that societies have been operating on and force a fundamental re-examination of them. The hidden assumption that this event would expose most brutally is our assumption of solar permanence. We build our civilization, our agriculture, our energy systems, our cities, our calendars, our religions, our philosophies, on the assumption that the sun will rise tomorrow. We have never, in the entire history of human civilization, had reason to seriously question that assumption. We have watched the sun set thousands of times and always trusted that it would rise again. It is perhaps the single most reliable fact in our lived experience. And in 24 hours, it would have been shattered. The question that would haunt humanity in the aftermath would not just be, what happened? It would be, what if it happens again? Because here is the uncomfortable truth. We do not fully understand what caused the hypothetical disappearance. In our thought experiment, we assume the sun simply disappeared and returned for 24 hours, without speculating about the mechanism. In the real world, any actual disappearance of the sun would require some physical explanation, and that explanation would determine whether it could happen again. If the sun could disappear once, arbitrarily, without warning, and return, then we would have to live with the knowledge that it could happen again at any moment. And that knowledge would fundamentally change civilization. The urgency of space exploration, of finding alternative energy sources, of understanding the physics of our star, would become existential rather than merely scientific. The investment in nuclear fusion, in alternative energy, in space colonization, would surge, not out of ambition or curiosity, but out of fear, out of the recognition that we are dependent on a single star in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, and that dependence is a vulnerability. It is an existential risk that we have never had to truly reckon with before. Let us now indulge in some more specific and targeted speculation about what the scientific community would discover in the aftermath of the 24-hour blackout. Because science does not stop during a crisis. In some ways, it accelerates. The instruments that were running during those 24 hours, the seismographs, the atmospheric monitors, the satellite sensors, the gravitational wave detectors, the radio telescopes, would have recorded data unlike any that has ever been collected. And sorting through that data in the weeks and months afterward would be one of the most extraordinary scientific endeavors in history. What might scientists find? Consider the gravitational wave data. If LIGO and Virgo detected the gravitational signature of the sun's disappearance and subsequent reappearance, the shape of those signals would tell physicists something extraordinary. They would tell us about the mechanism of the disappearance, about the rate at which the sun's mass was removed from its location, about whether the disappearance was instantaneous or gradual. This would be extraordinary data for testing the predictions of general relativity in a regime that has never been experimentally accessible before. Consider the atmospheric data. The patterns of temperature change, wind change, precipitation change during the 24 hours would be an extraordinary natural experiment, providing climate scientists with data about how the atmosphere responds to sudden removal of solar forcing. This is actually one of the most difficult things to study under normal conditions, because the solar forcing is always there, always present, and we can only study its effects indirectly. A 24-hour natural experiment with the sun removed would provide data that would fundamentally advance our understanding of the climate system. Consider the biological data. How did species respond? What happened to migration patterns, breeding behaviors, ecological interactions? How did ecosystems recover in the weeks and months afterward? What species turned out to be more resilient than predicted? What species were more vulnerable? The ecological data from a 24-hour global darkness event would be of incalculable scientific value. And consider the psychological data. The mental health records, the social media analytics, the behavioral studies that would follow would constitute the largest natural experiment in human psychology ever conducted. How did different cultures respond differently? What individual characteristics predicted resilience versus breakdown? What social structures proved most supportive in the crisis? This data would have enormous implications for emergency preparedness, for mental health policy, for our understanding of human nature under extreme stress. In the months following the event, an entirely new field of scientific inquiry might emerge. Call it, speculatively, solar absence research. A field dedicated to understanding the full system-level consequences of solar irradiance changes on Earth, using the extraordinary dataset provided by the blackout as its foundational empirical basis. This field might bring together astrophysicists, climate scientists, ecologists, psychologists, economists, and sociologists in ways that had never been attempted before. The event, as devastating as it was, would be a gift to science of a kind that could never be ethically manufactured in any laboratory. Let us now zoom out further to the grandest possible scale and think about what this thought experiment tells us about our place in the cosmos. Because one of the most valuable things about thought experiments is not the specific answers they provide, but the perspective they generate. And the perspective generated by even 30 minutes of serious thought about what would happen if the sun disappeared is genuinely vertiginous. We live on a rocky ball, 8,000 miles across, orbiting a medium-sized star, in the outer arm of a galaxy containing roughly 200 billion other stars, in a universe containing an estimated 2 trillion galaxies. We are not at the center of anything. We are not in a privileged location. We are not especially large or especially significant by any objective cosmic measure. And our continued existence, the existence of every human being who has ever lived or will ever live, the existence of every work of art, every scientific discovery, every love story, every moment of beauty or kindness or courage, is dependent on the continued functioning of a single, specific, medium-sized star. That star is 4.6 billion years old. It will live for approximately another 5 billion years before it begins to expand into a red giant and ultimately, billions of years from now, engulf the inner planets including Earth. In the long run, the sun will kill us. Not today. Not for billions of years. But the same sun that is the source of all life on Earth is also, in the long run, the death sentence of all life on Earth. Unless we have left by then. Unless, in the next few billion years, we have managed to spread life to other star systems, to find new suns, to make ourselves something other than a one-star species. The thought experiment of the sun's 24-hour disappearance is, at its deepest level, a meditation on this dependency. It forces us to confront the fact that we are, right now, completely and totally dependent on a single astronomical object for every aspect of our existence. And it asks us, implicitly, whether that is a situation we should accept indefinitely, or whether it is a challenge we should rise to meet. There is a concept in astronomy called the habitable zone, sometimes romantically called the Goldilocks zone. It refers to the range of orbital distances from a star at which liquid water can exist on a planet's surface. Not too hot, not too cold. Just right. Earth is in the habitable zone of our sun. This is one of the necessary conditions for life as we know it. But the thought experiment reveals something that the habitable zone concept quietly glosses over. Being in the habitable zone is not just a matter of distance. It is a matter of consistency, of the star reliably doing what it is supposed to do, day after day, year after year, century after century. A star that occasionally disappeared for 24 hours would not be a good candidate for hosting a stable biosphere, regardless of its average energy output. The sun's extraordinary stability is, in fact, one of its most remarkable features and one of the most important conditions for the origin of complex life on Earth. Compared to many other types of stars, the sun is a remarkably quiet, stable, well-behaved star. It has relatively few dramatic flares. Its output varies by only about 0.1% over its 11-year solar cycle. It has been shining steadily for 4.5 billion years, providing the constant, reliable energy input that allowed complex life to evolve, and then to persist long enough to develop intelligence. Many other stars are far more variable, far more prone to violent flares, far less reliable. The sun's stability is not something we usually stop to be grateful for, but we should be. It is as important to our existence as the sun's energy output itself. Now let us turn our attention to something that is genuinely mysterious and that the scientific community is actively wrestling with. The question of solar minimums and what they can tell us about a world with significantly reduced solar output. Because while the complete disappearance of the sun is a thought experiment, significant reductions in solar output have actually happened in the recorded history of human civilization, and their consequences are both fascinating and cautionary. The most famous and well-documented of these is the Maunder minimum, a period roughly between 1645 and 1715 during which sunspot activity on the sun essentially ceased. Sunspots are regions of intense magnetic activity on the sun's surface, and their frequency is tied to the overall energy output of the sun. During the Maunder minimum, the reduction in solar output, though relatively small by astronomical standards, perhaps a fraction of a percent, the Little Ice Age saw rivers in northern Europe freeze that had never frozen in recorded history. The Thames in London froze solid enough to hold frost fairs, carnivals, and markets held on the ice. In the Alps, glaciers advanced dramatically, threatening and in some cases overrunning villages. Agricultural output dropped. Famines occurred. The bubonic plague found a weakened, cold-stressed population more vulnerable to its ravages. The French Revolution has been linked by some historians to the economic stresses created by the poor harvests of the Little Ice Age. Even the creative output of the era was shaped by it. The Baroque music of the period, with its dramatic contrasts and emotional intensity, has been poetically linked by some musicologists to the harsh and dramatic climate of the time. Now, the Maunder minimum was not a disappearance of the sun. It was a tiny reduction in output, a fraction of a percent, over decades. And yet its effects were significant enough to alter the course of history. This should give us pause when we think about what a 24-hour complete absence would mean. The Maunder minimum, with its tiny, gradual reduction in solar energy, reshaped civilizations. A 24-hour complete absence, even though it is followed by the sun's return, would be 1,000 times more dramatic in its immediate physical effects. There is another historical analog worth considering. The year without a summer in 1816. This was caused not by a change in the sun itself, but by the eruption of Mount Tambora in Indonesia in April 1815, the largest volcanic eruption in recorded human history. The eruption injected enormous quantities of sulfur dioxide and ash into the stratosphere, creating a veil that reflected sunlight back into space and reduced solar irradiance reaching the Earth's surface by an estimated fraction of a percent. The result was the coldest year in recorded history in many parts of the Northern Hemisphere. Crop failures across Europe and North America. Famine in Ireland and Germany. Tens of thousands of deaths. And something even more interesting happened in that strange, dark, cold summer of 1816. One of the greatest works of Gothic literature in history was born. A group of young writers, including Mary Godwin, who would become Mary Shelley, and Lord Byron, were gathered at a villa on Lake Geneva in Switzerland. The weather was so cold and dark and dreary that they could not go outside. So they stayed in and told each other ghost stories. And in that summer of volcanic darkness, Mary Shelley conceived Frankenstein, one of the most influential works of fiction ever written. A story about the consequences of creating life without understanding its implications, about the hubris of science disconnected from empathy, about the loneliness of being something new in a world that does not know what to make of you. What stories, what works of art, what philosophical and scientific ideas might be born in the darkness of 24 hours without the sun? What would people think about, alone in the dark, waiting for the light to return? What would they write? What would they say to each other? What would they pray for? What would they promise themselves and each other? The cultural consequences of this event, its impact on literature, on music, on religion, on philosophy, would be as profound as its physical consequences. Perhaps more so. The physical damage, extensive as it would be, would eventually heal. The cultural impact, the permanent alteration of how human beings think about the sun, about the cosmos, about their own vulnerability, might be the most lasting legacy of all. And now let us think about something that rarely comes up in scientific discussions of the scenario, but that is, in many ways, the most important thing to understand. Let us think about what this scenario teaches us about the nature of uncertainty and about how human beings live with it. Because here is the thing. Right now, today, as you are listening to this, there are things happening in the universe that will affect the Earth and everything on it that we do not know about, that we cannot predict, and that we have no control over. Not the disappearance of the sun, which is not going to happen, but other things. The occasional giant solar flare that could fry our satellites and power grids. The near-Earth asteroids that we have not yet catalogued. The slow, long-term changes in the sun's output as it ages. The geological processes that are reshaping the Earth's surface on timescales we can barely comprehend. We live in a universe of genuine uncertainty. We live on a planet that is, in astronomical terms, neither safe nor stable, but has simply been lucky enough to be quiet for long enough to allow complex life to emerge and thrive. The thought experiment of the sun's disappearance is, at its heart, an invitation to look at that uncertainty honestly, to acknowledge the contingency of our existence, and to ask what we want to do with the time and the light that we have. Because the sun will not disappear tomorrow, almost certainly, but the recognition that we are dependent on it, that everything we love and everything we are is built on the light of a single, specific, unremarkable star, is not a cause for despair. It is a cause for wonder, for gratitude, for the kind of deep, resonant appreciation that you feel when you understand how improbable something beautiful is. Physicists sometimes talk about something called the fine-tuning problem. The observation that the fundamental constants of the universe, the strength of gravity, the electromagnetic force, the mass of the electron, the speed of light, seem to be tuned with extraordinary precision to values that allow matter to form, stars to shine, and chemistry to give rise to life. Change any of these constants by even a small amount, and the universe becomes sterile. No stars, no planets, no chemistry, no life. The universe appears to be extraordinarily precisely calibrated to allow us to exist. Whether this is evidence of design, of multiverse selection, or simply of the anthropic principle, the observation that we naturally find ourselves in a universe compatible with our existence is one of the great debates of modern cosmology. What the sun's disappearance thought experiment adds to this conversation is a sense of scale. Even within a universe that is fine-tuned to allow stars to shine and life to emerge, the particular local conditions that allow our particular form of complex life on this particular planet are extraordinarily specific and extraordinarily fragile. The right kind of star, stable enough, long-lived enough. The right orbital distance. The right planetary size, large enough to hold an atmosphere but not so large as to be a gas giant. The right axial tilt, giving us seasons but not extremes. The right magnetic field, protecting us from the solar wind. The right moon, large enough to stabilize our axial tilt. The right composition of the atmosphere. The right chemical inventory in the primordial ocean. Each of these conditions is independently remarkable. Together, they constitute a chain of extraordinary improbability. And the sun, present every day of every year for 4.5 billion years, is the foundation on which every other condition rests. Pull it away for 24 hours, and you can see, in the sudden rushing cold and dark, just how extraordinary and how precarious that foundation actually is. Let us now discuss what many scientists consider to be one of the most fascinating and underappreciated dimensions of the relationship between Earth and the Sun. The story of how life on Earth has not merely been sustained by the Sun, but has actively co-evolved with it, been shaped by changes in solar output over billions of years. Because the Sun we have today is not the Sun of the early Earth. The Sun 4.5 billion years ago was about 30% dimmer than it is today. It has been gradually brightening ever since, at a rate of roughly 1% per 100 million years. This raises a fascinating paradox called the faint young sun paradox. The geological record shows clear evidence that the early Earth had liquid water on its surface, even as far back as 4 billion years ago. But if the Sun was 30% dimmer 4 billion years ago, simple calculations show that the Earth's surface should have been completely frozen. The amount of solar energy reaching early Earth should have been insufficient to prevent a global glaciation. And yet the rock record shows liquid water. Sedimentary rocks laid down in ancient rivers and lakes. Chemical signatures of aqueous chemistry. How? The most compelling explanation is that the early atmosphere was much richer in greenhouse gases than today's, particularly carbon dioxide and methane. These gases would have trapped enough of the sun's dimmer radiation to keep the surface above freezing. As the sun gradually brightened over billions of years, geological processes, particularly the long-term carbon cycle, gradually reduced the concentration of greenhouse gases in the atmosphere, keeping the planet's temperature relatively stable even as the sun's output increased. It is an extraordinary example of planetary-scale self-regulation, the Earth's chemistry adjusting to compensate for changes in its star, maintaining the narrow temperature range in which liquid water and life can persist. This is the Gaia hypothesis territory, though the scientific community prefers the more rigorously framed Earth system science that has grown from James Lovelock and Lynn Margulis's original insights. The idea that the Earth is not a passive object being acted upon by the Sun, but an active, self-regulating system that modifies its own atmosphere, its own surface chemistry, its own climate, in ways that tend to maintain conditions compatible with life. Not through intention or consciousness, but through the emergent dynamics of billions of interacting organisms and geological processes. The disappearance of the Sun for 24 hours would be a test of this self-regulatory capacity. Could the Earth system respond? In 24 hours, the answer is largely yes. The thermal inertia of the system is large enough to buffer against such a short disruption. But the self-regulatory processes, the carbon cycle, the water cycle, the biological feedbacks, all operate on timescales of decades to millions of years. They are not designed for a 24-hour perturbation. In 24 hours, the Earth system would experience the perturbation without having any meaningful time to respond to it. It would just have to endure it, and then recover in the aftermath. And the recovery, as we noted, would take longer than the event itself. Ecosystems would be recovering for months. Some of the most sensitive environments, the tropical forests, the coral reefs, the high-altitude meadows, might take years to fully return to their pre-event state. This asymmetry between the speed of damage and the speed of recovery is one of the most important general principles in ecology. It is the same principle that makes forest fires recoverable but extinction permanent. Damage is fast. Recovery is slow. And some damage is so severe that recovery never fully occurs. We should also, in this context, discuss the ocean. Because the ocean is perhaps the most important long-term reservoir in the Earth system, and its response to 24 hours of darkness would be both complex and consequential. The ocean surface, as we noted, would cool more slowly than the land surface. But even a small amount of surface cooling has implications for the biological productivity of the ocean. The most biologically productive parts of the ocean are not the warm, clear tropical waters, which are actually biological deserts. The most productive parts are where cold, nutrient-rich deep water wells up to the surface, bringing with it the minerals and compounds that phytoplankton need to grow. The temperature differentials created by the 24-hour darkness would alter the patterns of ocean circulation. Some upwelling zones might be temporarily enhanced, bringing more nutrients to the surface. Others might be temporarily suppressed. The net effect on ocean biological productivity over the weeks and months following the event would be complex and difficult to predict. But what seems clear is that the phytoplankton, the foundation of the marine food web and the producers of most of Earth's oxygen, would experience a period of disruption that would have cascading effects through every level of the marine ecosystem. And here is something truly extraordinary to consider. The phytoplankton are not just oxygen producers. They are also carbon sinks. They absorb enormous quantities of carbon dioxide from the atmosphere during photosynthesis. And when they die, their carbon-rich bodies sink to the ocean floor, where the carbon is stored for millions of years. This is called the biological carbon pump, and it is one of the most important mechanisms regulating the concentration of carbon dioxide in the Earth's atmosphere. Disrupt the phytoplankton, and you disrupt the biological carbon pump. Even a temporary disruption could leave a measurable signature in the atmospheric carbon dioxide record. After the event, as the phytoplankton recovered and their productivity returned to normal, there might actually be a brief surge in photosynthetic activity, as the surviving phytoplankton in newly nutrient-rich waters bloomed and spread. These phytoplankton blooms would consume carbon dioxide at an elevated rate for a period of weeks to months. The net effect on atmospheric carbon dioxide might actually be a temporary reduction, as the post-event bloom sucked more carbon out of the atmosphere than had been released during the disruption. This would be a tiny effect, barely measurable by current instruments. But it would be there. A subtle chemical fingerprint of the event, written in the atmosphere for decades to come. Now let us address something that has been implicit in everything we have discussed, but that we have not yet stated directly. Something about the nature of light itself that this thought experiment illuminates in a way that is almost unbearably beautiful. Light is not just a source of energy. Light is information. Light is the primary medium by which we, and every other sensing organism on this planet, know anything about the world beyond our immediate physical contact. We see by light. We navigate by light. We communicate with light using fire, electrical lights, and now lasers and fiber optics. We understand the universe by light because it is the light from distant stars and galaxies that carries to us all of the information we have ever gathered about the cosmos. The famous equation E=mc² tells us that energy and matter are interchangeable, that mass is a form of frozen energy. But there is another equation, less famous but equally profound, that tells us that information and entropy are linked, that the universe tends towards states of greater disorder, greater entropy, and that information is, in a deep thermodynamic sense, a form of order. When you think about photons of light as not just energy but information, as packets of data encoding the state of their source at the moment of emission, the universe takes on a new character. The universe is a vast communication network. Every star is constantly broadcasting its current state, its temperature, its composition, its velocity, its age, in the form of photons radiating outward in every direction. And every planet, every moon, every dust grain in space is constantly receiving this information, this light, from every direction. The Earth is bathed in information from across the cosmos. And we, with our eyes and our telescopes and our radio dishes, are reading it. We are the universe's most sophisticated information processing systems. We are the universe reading itself. In those 8 minutes and 20 seconds before the last photon of sunlight reached Earth, we would have been reading information from a source that no longer existed. We would have been receiving messages from the dead. Or rather, the dead would have been sending us messages from 8 minutes in the past, the only way the universe allows. And we would not have known. We would have thought we were in the present, when in fact we were receiving the last broadcasts from a past that had already been erased. This is not just a technical point about the speed of light. It is a revelation about the nature of knowledge and reality. We never know the present state of anything at a distance. We always know only the past state. We always live on a kind of informational delay, cut off from the true present of everything more than a few nanoseconds away from us. The further away something is, the further into its past we are seeing. And in a universe where everything is at some distance from everything else, there is no true present. There is only the past, propagating toward us at the speed of light. Think about the implications of this for our sense of connection to the cosmos. The star you love to look at on summer nights, perhaps Vega, perhaps Sirius, perhaps Betelgeuse, is not there now. Not in the sense of now that you mean when you say now. The light from Vega takes about 25 years to reach us. The Vega you see tonight is Vega 25 years ago. Sirius, 8.5 light years away, is Sirius 8.5 years ago. And Betelgeuse, the red supergiant in Orion, is about 700 light years away. The Betelgeuse you see tonight is Betelgeuse in the medieval period, more than 700 years ago. That star might have already gone supernova. We would not know for centuries. Every time you look at the night sky, you are looking at history. The sky is a time machine. Every direction you look is a different moment in the past, and the further you look, the further back you go. The farthest objects we have ever seen with our telescopes, galaxies at the edge of the observable universe, are seen as they were 13 billion years ago, when the universe was only a few 100 million years old. We are seeing the infancy of the universe, and we are looking at it now, from the present, as we stand on a planet orbiting a star in a galaxy in a universe that is now 13.8 billion years old. The thought experiment of the sun's disappearance, with its 8-minute and 20-second delay between event and knowledge, is a tiny, personal-scale demonstration of this cosmic reality. It makes abstract the concrete and makes the concrete abstract. It takes the enormous philosophical fact of the finite speed of information and brings it home, makes it visceral, makes it matter in a way that the abstract knowledge of light years and light years of distance does not quite manage. Let us return to Earth one more time, to the immediate reality of the 24-hour event, and let us think about one more dimension of it that we have not yet fully explored. Let us talk about what happens in space. Not in the universe at large, but in the immediate vicinity of Earth. In low Earth orbit, in the space stations and satellites that are now an indispensable part of modern civilization. The International Space Station orbits Earth at an altitude of about 400 kilometers. In low Earth orbit, the station passes through both the lit side and the dark side of the planet every 90 minutes. The station generates its electricity from large solar panels, converting sunlight into power that runs all of its life support systems, its science instruments, its communication systems. Without sunlight, those solar panels go dark. The station has batteries and fuel cells to bridge the gap during the regular nighttime passes, but these are not designed to sustain the station through a 24-hour absence of sunlight. The crew of the International Space Station, along with the crews of any other crewed spacecraft in orbit at the time, would be in immediate danger. Life support would fail within hours as battery reserves depleted. The station would begin to cool as its thermal regulation systems, which use solar energy, stopped working. Communication with the ground would become erratic and then fail. The crew would face an extraordinary decision. They could attempt to conserve power by shutting down all non-essential systems, including most of the life support redundancy, hoping to stretch the battery reserves long enough to survive until the sun returned. Or they could attempt a rapid evacuation to Earth, using the Soyuz or Crew Dragon vehicles docked to the station. But re-entry requires precise guidance and navigation systems that depend on power and communication with the ground, which itself would be experiencing enormous stress. The situation for the crew of the ISS would be one of the most acutely dangerous in the entire 24-hour scenario. 6 human beings, sealed in a metal shell 400 kilometers above the Earth's surface, watching their power reserves tick down, watching the thermometers drop, watching the sun not come up, knowing that if it did not come back in time they would simply run out of power and life support, and that would be the end. The satellites, the tens of thousands of satellites in various orbits around Earth, would face a similar power crisis. Communication satellites, GPS satellites, weather satellites, Earth observation satellites, all powered primarily by solar panels, all going dark simultaneously. The GPS system would fail. Navigation for ships, planes, vehicles, personal devices would be lost. Internet services delivered by satellite would fail. Military communication and surveillance systems would be degraded. The knock-on effects of satellite failure on terrestrial systems would be enormous, because modern civilization has become deeply, perhaps dangerously, dependent on satellite services that we rarely think about until they are gone. And the satellites in geostationary orbit, those at an altitude of 36,000 kilometers that orbit Earth at the same rate Earth rotates and thus appear stationary over a fixed point on the surface, the satellites that carry most of the world's broadcast television and weather monitoring capabilities, would simply drift off their station-keeping positions as their thrusters ran out of power and they lost their ability to correct for the various perturbations that constantly push them off course. The total value of the world's satellite fleet is estimated at hundreds of billions of dollars. The loss of GPS alone, for 24 hours, would cause economic disruption estimated in the hundreds of billions more. Modern logistics, modern financial systems, modern military operations, all depend on precise GPS timing and positioning in ways that are not widely understood. The GPS system provides not just navigation, but also extremely precise timing signals that are used to synchronize financial transactions, power grid management, cellular networks, and internet routing. Lose GPS, and all of these systems become less reliable simultaneously. Now let us think about something that runs counter to the fear and chaos we have been describing. let us think about what is remarkably resilient. Because this is actually one of the most important and most scientifically interesting aspects of the scenario, and it tends to be neglected in favor of the dramatic catalog of disasters. Because even in 24 hours without the sun, the extraordinary resilience of life, of human civilization, and of Earth systems would be on full display. Life on Earth has survived far worse. The history of life on this planet is a history of mass extinctions, of catastrophic events that killed off enormous proportions of all species, and then of recovery. Life has survived impacts of enormous asteroids, supervolcanic eruptions that lasted millions of years, dramatic changes in atmospheric chemistry, dramatic changes in climate. Life has always come back. Not the same life, not the same species, but life. The fundamental capacity of living systems to persist, to adapt, to evolve, to find new ways of exploiting available energy, has proven to be one of the most robust features of the universe we live in. 24 hours without the sun would be, by the standards of Earth's history, an extraordinarily brief perturbation. Less than the blink of an eye. The vast majority of life on Earth would survive. The vast majority of human civilization would survive. The physical infrastructure, the buildings, the roads, the communication networks would be mostly intact. The knowledge, the science, the culture, the art, the libraries and the databases and the accumulated wisdom of human civilization would be preserved. The lights would come back on. The plants would start photosynthesizing. The temperature would start climbing back toward normal. Life would go on. But something would have changed, not just in the physical world, but in the human mind, in the collective consciousness of a species that had, for a day, been forced to confront its own vulnerability. The 24 hours of darkness would be, in the history of human psychology, one of the most significant events ever experienced. A collective trauma, yes, but also, potentially, a collective awakening. A moment when billions of people were simultaneously forced to look up at a sky where the sun should be and was not, and to feel, in their bones, the silence of a cosmos that did not particularly care about their comfort or their survival. And in that silence, some of them would find something. Not despair, not faith, necessarily, though some would, but something more fundamental. A clarity about what matters. About what is irreplaceable, about who they want to be in the dark, when the ordinary structures of daily life fall away and what is left is just the human animal, frightened and alive and reaching for the warmth of another person. There is a famous experiment in social psychology, the darkroom experiment, in which groups of strangers were put in a completely darkened room for extended periods. The consistent finding across multiple replications was that darkness dramatically increased social bonding. People became more cooperative, more empathetic, more willing to share personal information and emotional vulnerability. The barriers that maintained social distance in well-lit, formal settings dissolved in the dark. People reached for each other, not just physically but emotionally. They talked more honestly. They listened more carefully. They were kinder. It would be romantically irresponsible to claim that 24 hours of global darkness would transform humanity into a more loving and cooperative species. Human nature is not so easily overwritten by a single experience. The conflicts and inequalities and grievances that structure human society would return with the light. They always do. But perhaps, in the weeks and months after the sun came back, there might be a residue. A slightly greater appreciation for the ordinary miracle of sunlight. A slightly greater awareness of interdependence and fragility. A slightly reduced tendency to take for granted the constant, reliable, magnificent presence of the star that makes all of this possible. The ancient Egyptians, who built one of the greatest civilizations in human history, organized their entire world around the sun. The pharaoh was the son of Ra, the sun god. The great temples were aligned to the sun's path. The agricultural calendar was calibrated to the Nile flood, which was itself driven by the monsoon system, which was driven by solar heating. The daily movement of the sun across the sky was the central organizing fact of Egyptian cosmology. When Ra set in the west each evening, the ancient Egyptians believed he was making a perilous journey through the underworld, navigating dangers, fighting demons, before rising again in the east each morning. The sunrise was not taken for granted. It was celebrated, prayed for, honored. It was understood as a daily miracle, fragile and precious. We have forgotten that. We turn off the alarm, we make the coffee, we go about our day, and the sun is just there. Background noise. Wallpaper. The unremarkable constant hum of the cosmic engine. We don't celebrate sunrise. Most of us have not watched a sunrise in years. We have lost the ancient understanding that the return of the sun is a gift, contingent and precious, not a given. 24 hours without the sun would, perhaps more effectively than any philosophy or any religion or any scientific education, restore that understanding. Not theoretically, not intellectually, but in the blood and the bone. In the shivering, dark-adapted body that stood at the window and watched the sky go black where it had been blue. In the heart that leapt, physically leapt, when the first photons appeared on the horizon and the world began to lighten again. The return of the light would be one of the most emotionally powerful moments in human history. Every person who witnessed it, and most of the 8 billion people alive at that moment, would be awake and aware, having been far too frightened to sleep, would remember it for the rest of their lives. Where they were, who they were with, what they felt. The tears, the laughter, the screaming, the prayer, the stunned silence. The way the light crept back, tentative at first, and then certain, flooding the world back to color and warmth and meaning. Artists would spend the rest of their lives trying to capture that moment. Writers would build careers around it. Theologians would debate its implications for decades. Scientists would study it for generations. And children born after it would grow up in a world subtly but permanently changed by it. A world that remembered, in a way it had not before, that the sun is not automatic, that the light is not guaranteed, that every morning is a small miracle. Let us end our journey through this thought experiment by asking the question that, in some ways, is the most important of all. Not what would happen if the sun disappeared for 24 hours, but what should we do with the knowledge that we have explored today? What does this thought experiment, honestly engaged with, demand of us? It demands, first, that we take seriously the scientific imperative to understand our star. We know a great deal about the sun. We have sent probes to study it, including the Parker Solar Probe, which as of the time of this production has made the closest approaches to the sun of any human-made object, flying through the solar corona and gathering extraordinary data about the sun's most energetic and dynamic outer atmosphere. We have solar observatories in space, including the Solar and Heliospheric Observatory, SOHO, which has been continuously monitoring the sun since 1995. We understand the broad strokes of solar physics better than ever before. But there is still so much we do not know. We do not fully understand why the sun's corona, its outer atmosphere, is millions of degrees hotter than its surface, which is only about 5,500 degrees Celsius. The corona is 2 million degrees Celsius. By the laws of thermodynamics, heat should not flow from a cooler surface to a hotter atmosphere. Something is heating the corona from above, or from the surface, using a mechanism that we have not yet fully identified. We do not fully understand what drives the 11-year solar cycle of sunspot activity, or what determines the intensity of individual solar cycles. We cannot yet reliably predict solar storms or massive coronal mass ejections with the kind of advance warning that would allow us to protect our increasingly satellite-dependent civilization. These are not trivial gaps. A large enough coronal mass ejection, a Carrington-class event like the solar superstorm of 1859, could today destroy a significant fraction of the world's satellite fleet and cause widespread power grid failures. The Carrington event, in 1859, induced such powerful electrical currents in the telegraph wires of the time that some telegraph operators reported receiving shocks, and some telegraph stations caught fire. If a Carrington-class event happened today, the damage to our satellite and power infrastructure could run into the trillions of dollars and could take years to repair. This is a real risk, not a thought experiment. And our ability to predict and prepare for it depends on our understanding of the sun. The thought experiment demands, second, that we take seriously the project of reducing our dependence on a single source of energy. Not because the sun is unreliable, it is extraordinarily reliable, but because the recognition that all of our energy ultimately comes from the sun should motivate us to diversify. To invest in nuclear fusion, which, if successful, would give us a sun on Earth, a controlled, sustained source of energy that mimics the sun's fundamental process. To invest in better energy storage, so that the interruption of solar energy at night or during cloudy periods does not create vulnerability. To invest in space-based solar power, which could capture sunlight above the atmosphere, where it is far more intense and uninterrupted, and beam it to Earth as microwaves or lasers. And the thought experiment demands, third, something more personal. Something less about policy and more about the texture of daily life. It demands that we look up, more often, at the sun. Not directly, never directly with the naked eye, but at the light it creates, at the quality of the illumination it provides at different times of day. At the way morning light is different from afternoon light is different from evening light. At the way clouds scatter and diffuse and color it. At the way seasons shift the angle at which it strikes the earth and change the character of everything it touches. We live immersed in one of the universe's most remarkable phenomena, a sustained thermonuclear reaction 400,000 times more massive than the Earth, perfectly calibrated by its own dynamics to provide a steady, reliable, life-sustaining output for billions of years, shining at just the right intensity from just the right distance. And we mostly ignore it. We close the blinds because the glare is annoying. We complain when it is too hot. We forget, completely and routinely, that without it, we would not exist. That without it, every single thing we love, everyone we know, every experience we have ever had, every dream we have ever dreamed, would be impossible. The ancient Aztec priests understood something that we have lost. They believed, with absolute seriousness, that the sun needed to be fed, that it required the energy of human sacrifice, the most precious offering they could conceive of, to keep burning, to keep moving across the sky, to keep rising each morning. They were wrong about the mechanism. Horrifically, tragically wrong about the sacrifice. But they were right about the fundamental insight. The sun requires something from us. Not blood, but attention, gratitude, respect. The recognition that it is not automatic, not permanent, not guaranteed. That it is a gift, and that the right response to a gift of this magnitude is to notice it, to stand in it, to be grateful for it. You will not disappear the sun. The sun will not disappear. Not tomorrow, not in your lifetime, not in the lifetime of any human being who will ever live. But the understanding that you could, in principle, imagine a world without it, and that such a world would be cold and dark and terrifying and fragile, is itself a kind of illumination. A reminder of what you have. A reminder of what we all share. This star, this light, this warmth. Consider this. Every human being who has ever existed has lived under the same sun. Every civilization that has ever risen and fallen has been warmed by the same star. Every child who has ever chased a butterfly across a summer meadow, every sailor who has ever navigated by its position at noon, every farmer who has ever watched the sky and prayed for one more day of sunshine before the harvest, every painter who has ever tried to capture the way it turns everything gold in the late afternoon, every poet who has ever reached for words to describe what it feels like to walk out of a dark building into bright sunlight and feel the warmth on your face as a physical gift. All of them, all of us, children of the same sun. Sustained by the same light, connected across all of time and all of history by the simple, magnificent, unremarkable fact that the sun came up this morning. And if you take only one thing from this extraordinary exploration through physics and philosophy, through ecology and psychology, through history and speculation and wonder, let it be this. The next time you see the sunrise, and you will see it soon because the sun is still here and it will come up tomorrow just as it has come up every day of your life and every day of every human life before you. Stop for a moment. Just for a moment. Watch it. Feel it. Let yourself notice, consciously, deliberately, what it means. Let the light fall on your face and remember what you know now, that this light traveled 149 million kilometers in 8 minutes and 20 seconds to reach you, that it was generated by a thermonuclear reaction in the core of a star 4.5 billion years old, that it powered every bite of food you have ever eaten, that it is the reason there is oxygen in the air you are breathing right now, that it is the reason there is weather, why there are oceans, why there are forests, why there is birdsong and the smell of rain on hot pavement and the color of autumn leaves. And then, having noticed all of this, having sat for one morning in the full awareness of the sun's extraordinary and unremarkable miracle, go about your day, with the knowledge that you are not just a person living on a planet. You are a sunlit creature, soaked through with starlight, carrying in your body's chemistry the gift of 100 million years of photosynthesis, built from the stuff of stars, warmed by the nearest one of them. You are, in the most literal and most beautiful sense of the word, a child of the sun. And the sun, as far as we know, is not going anywhere. At least not for another 5 billion years. And in the meantime, the light is extraordinary. Go and stand in it. But wait, because there is one more thing. One more layer to this thought experiment that we have saved for last, because it is perhaps the most provocative and the most unsettling, and it deserves to be delivered with the weight of everything that has come before it. We have been assuming, throughout this entire exploration, that the disappearance of the sun for 24 hours would be an observable event, one that everyone on Earth would know about, one that would be visible and unmistakable and undeniable. We have been assuming that the darkness, the cold, the chaos would be shared, that everyone would be in it together. But here is the thing. Because of the finite speed of light, because of the 8-minute and 20-second delay, and because of the way information propagates across a spinning planet with different time zones and different levels of access to information, there is a small but philosophically fascinating window in which the event would be known by some people and not others. In those first 8 minutes and 20 seconds after the sun disappears, but before the last photon arrives at Earth, there would be no one on Earth who knew. And in the subsequent hours, as the darkness spread across the dayside and the world struggled to understand what was happening, there would be people in remote areas, people without access to communication networks, people who simply had not heard the news yet, who would experience the onset of darkness without knowing what it was or whether it was happening everywhere. They would be more alone with it than the rest of us, more isolated with their fear. And this points to something that the thought experiment, in all its scientific richness, ultimately circles back to: the profoundly human need to not be alone with a mystery. We can endure almost anything if we endure it together. We can face almost any fear if we face it with someone. The darkest moments in human history, the plagues, the wars, the famines, have always been made marginally more survivable by the extraordinary human capacity for solidarity, for community, for simply reaching through the darkness and touching the hand of another person. If the sun disappeared for 24 hours, the scientific consequences would be profound. The physical damage would be real and lasting. The economic cost would be staggering. But the deepest consequence, the most enduring one, might be the one that happened in the space between people. In the conversations held in the dark, in the hands held across kitchen tables lit by candles, in the texts sent to family members saying "I love you," "I'm okay," "Are you okay?" In the strangers who found each other sheltering in a doorway and decided to shelter together because the darkness was less frightening with company. And in the morning, when the light came back, those connections would remain. Some of them, at least. Some of the conversations started in the dark would continue in the light. Some of the walls that were down in the darkness would not go all the way back up. Some of the love that was expressed, impulsively, vulnerably, in the fear that the sun might not return, would discover that it had always been there, waiting for the dark to reveal it. That is perhaps the strangest and most beautiful truth that the disappearance of the sun could teach us. That sometimes it takes the loss of something you never thought you could lose to show you what you actually have. That sometimes it takes the dark to make you see the light. Not just the sun. All of it. The whole impossible, improbable, gorgeous, fragile, glorious mess of it. The sun is still there. It is still shining, even now. 8 minutes and 20 seconds ago, it was sending you this light, this warmth, this life. It did not know you were receiving it. It does not know you exist. It is a nuclear furnace in space, doing what nuclear furnaces do, indifferent and magnificent and eternal on a human timescale. But you know it exists. You know what it means. And now you know, in a way perhaps you did not before, what it would mean to lose it. And knowing that, you can choose to never lose it in another way. Never to stop seeing it. Never to stop standing in it. Never to stop being grateful for the fact that a medium-sized star in an unremarkable corner of the Milky Way has been shining steadily for 4.5 billion years, and will continue to shine for another 5 billion. And that by the most extraordinary coincidence or design or natural selection of observers in a multiverse, you exist, right now, in the thin habitable window of that star's long life, on a rocky planet at exactly the right distance, wrapped in exactly the right atmosphere, to receive its light and to know what it is and to love it for what it gives you. The sun is still there, and now you know what it means that it is. Let us, for a moment, sit with that, and then let us begin again, tomorrow, in the light. But before we do, one final question to carry with you. If you knew, with absolute certainty, that the sun was going to disappear for exactly 24 hours, starting tomorrow morning, what would you do today? What would you say, and to whom? Where would you go? What would you look at? What would you make sure to see, and smell, and feel, and experience in the last hours of sunlight before the darkness came? And what does the answer to that question tell you about what you should perhaps be doing right now, today, in the ordinary, unremarkable, magnificent sunlit world that you live in? Think about it. Sit with it. Let it change something. Because the sun is still here, and so are you. And that, if you let yourself feel it fully, is the most extraordinary thing in the world.